Oh, hey, Shelley.
Oh my gosh, Van, what is going on here? You look like you were in a food fight. You're on the losing side. What are you doing?
Well, I was baking some cookies for the NASA Connect cast party. They turned out kind of hard, though.
Oh, hard is an understatement. Van, you got some real problems here.
Well, I thought maybe you could give me a hand and figure out what I'm doing wrong.
Well, is this your recipe?
Right.
Well, I can hardly even read it.
Well, it's a copy of a copy of a copy that my great-grandmother wrote a long time ago.
Oh man, Van, you got some problems. But maybe. Right now, WVEC Channel 13, they have a daily cooking show, and if we are lucky, we may be able to actually catch the program and have something to help you with your problem.
Okay.
Coming to you from Hampton Roads, Virginia, and the WVEC Channel 13 studio, it's Cooking with the Stars with your host, Brittany Sudden.
Hi, everybody. With me is this week's co-host, Daphne Reed. Daphne, have you ever picked up a copy of Bon Appetit, saw a picture of a delicious loaf of bread, and said, hey, I can make that. All I have to do is follow the recipe. Well, you do, and guess what? It's not delicious. It's a disaster.
Yeah, that's what happened to us last time we made some bread. Last time we did our show on Italian food, this is what happened.
Yeah, I think the focaccia bread dough got the better of us.
Yeah, here to help us analyze the problem is a chemist from NASA Langley who specializes in developing recipes for future aerospace material. Our guest this week and our friend,
Dr. Catherine Fay. Hi, Catherine.
Hey, how are you?
Hey,
How are you doing?
that's Kathy Fay. I know her from work.
Catherine, great chefs are like, on some levels, great chemists. Now, we thought because you're a chemist, you might have some insight into what we did wrong last time.
Now, would you explain how a chemist follows a recipe?
Glad to help. For us at NASA Langley, our first step is to determine the requirements of the application. In your case, you need bread for an Italian meal. Making bread involves a chemical change. This is different from physical change, such as the boiling of water. That is, water becomes steam when heated, but when steam cools, it becomes liquid again. There is no change in the chemical identity of the substance. A chemical change or reaction involves the conversion of one substance into another. Mixing and baking bread is an example of a chemical change because the flour, sugar, and other ingredients are converted into a loaf of bread. Daphne, Brittany, having the proper ingredients is important. However, also knowing the properties of the ingredients is just as important in producing a successful recipe. Knowing the properties can also help you determine what went wrong. What were your ingredients?
We had flour, water, yeast, sugar, and salt.
Let's take a look at the properties of your ingredients. Flour contains gluten-forming proteins which allow the bread to rise. Water helps the gluten make the dough rise. Yeast causes the bread to rise and imparts flavor. Sugar provides food for the yeast, and salt slows the yeast activity. What was wrong with your bread?
Well, here's ours, and it sure looks like the bread didn't rise.
Now, I bought a loaf of focaccia this morning from the Chesapeake Bagel Bakery. Let's take a look at the difference here.
Wow.
What went wrong?
There are three possibilities. Too much salt, the yeast was dead, or insufficient rise time. A successful recipe is determined by using the proper ingredients, using the right amounts, mixing the ingredients properly, and heating and cooling as required. It's sort of like what we do at NASA Langley for recipes of materials used in airplane and space vehicle research. This means proper ingredients, correct processing, fabrication, and analysis.
Catherine, thanks for bringing some science to our show and helping us clear up our focaccia flop. Well, there you have it. The right recipe begins with the right ingredients.
Yeah, we've also learned from Catherine that knowing the properties of those ingredients can help the cook better predict what will happen when the ingredients are mixed, substituted, or changed.
Our cooking and yours is likely to be more successful when you know this, especially when you're trying to cook up a recipe for the future.
Van, I think Daphne Reed had a very important message there. Basically what she was saying is that a good cook is more than having just a recipe and the ingredients. A good cook is like a kitchen scientist.
Right.
You know what I mean? I mean, it's like you're gathering data from your cooking trials and then making informed decisions about what ingredients to use, how much to use, how to mix it up, and how to bake it. You know, I wonder if Dr. Kathy Fay at NASA Langley might be able to help us with your recipe.
Well, that'd be great. Maybe she could even help me rewrite my recipe. These cookies are just so hard and crumbling.
Oh, yeah. Okay, well, then let's do this. Why don't you stay here and clean this up? Get more ingredients out. Meanwhile, I'll head on over to NASA Langley, see if I can catch up with Kathy and her colleagues, because they're doing some really neat things with aerospace materials and structures. Matter of fact, they're really cooking up recipes for the future.
Well, you know, that sounds like a pretty good title for our NASA Connect show.
You're right. Hey, and gang, how about this? We'll leave him here. You and I, let's head on over to NASA Langley and see if we can find some things out there that's going to help Van in his recipe. We'll visit researchers at NASA Langley to learn more about the recipes they're cooking up for aerospace structures and materials, and we'll see if any of their steps might be helpful to Van, so take careful notes. And while we're at it, let's learn a thing or two about the composite materials NASA Langley is cooking up to build the airplanes and space vehicles of the future.
And as we go through the show, you'll be challenged by an experiment in composite materials that students performed at Hugo A. Owens Middle School in Chesapeake, Virginia. Oh, and when you see this banner, that's your clue to check out for more fun, information, and activities on the NASA Connect website.
That's right, and be thinking about questions during this program because you're going to have a chance to call in and email in questions to our NASA researchers. Hey, Van, let's get cracking.
Whoa.
Kathy, hello. Thanks for letting me come by here today.
Hi, Shelley, no trouble. This is my colleague, Roberto Cano from the Composites Fabrication Laboratory.
So nice to meet you. What's
Hi.
up?
Well, what's up is my friend Van Hughes. He's trying to cook something up and he's having a little problem with his cookie recipe. Seems that his cookies are way too hard. They're not chewy and they crumble very easily. Well, Kathy, we saw you today on the WVECU Cooking with the Stars program and thought maybe here at NASA Langley, where you are involved with the Composite Materials Laboratory, that there might be a recipe that you have that could help us, or some things that you do that could give us some advice to help Van in his problem.
Bert and I would be glad to help. In fact, the process that Bert and I follow in the Composites Fabrication Laboratory might offer a solution to Van's problem.
Oh, that's great. But now I got a question. What is a composite material, and just how is a composite material made?
A composite material is made of two or more different materials. Composite materials have been used throughout history. For instance, ancient Egyptians used a very basic composite material in the construction of their houses, straw and mud. They combined these two materials to make a third, stronger one, bricks. One of our goals at NASA Langley is to develop stronger, more durable, lighter weight materials for use on airplanes and space vehicles. NASA Langley Research Center is the agency's center of excellence for structures and materials research. We can identify 5 steps in composite development. Van may use similar steps in planning and preparing a cooking recipe. Identify the application, develop materials to meet requirements, process the material, test the material, and make structural components.
Okay, how about it? Could you give me some examples of how these steps work for composite development?
Glad to. Let me explain the first step. NASA has challenged their researchers to find ways to make planes and space vehicles tougher, stronger, lighter, cheaper. Our job as researchers is to develop new materials or to improve on existing materials. My work at NASA Langley involves development and characterization of polymers. A polymer is a huge chain-like molecule built up by the repetition of small, simple chemical units. Polymers can be flexible or stiff, tough or brittle, strong but lightweight.
Okay, so what's the next step?
Well, for a structural application, the polymer needs to be reinforced. Typically, this is done with a carbon fiber. And one way we combine the carbon fiber with the polymer is to make a prepreg tape.
Prepreg tape?
Well, let me show you what I mean. The principle of prepregging goes back to the early days of aviation. The planes were made of a wood structure covered with a skin of fabric coated with glue. This combination of the glue and the fabric was a form of composite material. We developed a prepreg material that combines the NASA Langley developed resin system PETI 5 with the carbon fiber IM7. This material was developed for applications for commercial supersonic aircraft. To fabricate IM7 PETI 5 prepreg, many ends of IM7 carbon fiber are introduced into a dip pan. In the dip pan, the fibers go over and under a series of bars. When the resin solution is poured into the pan, the bars help force the resin into the fiber bundles. The now coated fibers exit the pan and go through a series of ovens and nip rollers. The oven and nip rollers process the material into a uniform tape that is taken up at the end. This tape is referred to as prepreg and can now be used to make composite parts. As layers of the new material are processed together, it creates a tough structure that is lighter than metal but is strong and is stiff.
Well, this has been fascinating, but what pointers might you be able to give to me so I can pass on to Van with his cooking problem?
Given that Van's requirements are soft and chewy cookies, I recommend using half butter and half Crisco, baking the cookies at 350 degrees Fahrenheit in a preheated oven for about 8 to 12 minutes.
Also, to make the cookies more chewy, he could add oatmeal, raisins, or chocolate chips. But also, when you make a composite material, you need to test it to see how well it performs. So I would recommend that Van test his cookies before he serves them to anyone.
Shelley, I'd recommend you talk to David McGowan and Dr. Ted Johnson. They have a lot of experience in area testing.
Fantastic. I'm going to give Van a call with the information that you've shared with me. Then I'm going to be on my way. So thanks so much for all your help today. Appreciate it.
You're welcome.
Okay, Van, did you get all that?
I've figured out some of the ingredients, and now all I have to figure out is the quantity of the ingredients. And then I'll follow some of Kathy and Roberto's ideas on the oven temperature, baking time, and the properties.
Okay, great, Van. Meanwhile, I'm going to head on over to the materials testing and see what I can find out, and I'll give you a call back.
Oh, okay, but it smells like I have some butter burning on the stove, so I'll talk to you later. Whew.
Hi, Ted, Dave.
Hi, Kathy called and said you'd be coming over.
Seems like your friend Van has to test out his cookie recipe.
Yes, Van has a little problem. He's trying to get a cookie that tastes good, is chewy, and he doesn't crumble. So I thought maybe if I came over here and saw the process to testing new materials, maybe there's something I could learn from this to share with Van. Do you think you could help?
I think so. Ted and I both test and analyze structures for new aerospace and space vehicles. I usually test them at room temperature, and Ted actually tests them at extreme temperatures. Since I usually test at room temperature, the components that I test are larger than those that Ted uses in his thermal structural tests. What typically happens here is the component of the vehicle structure that we're interested in is built and shipped to our labs. We then apply sensors to it to help us understand how it behaves under different loads or forces. This panel here is part of the keel or bottom section of a high-speed civil transport supersonic aircraft. This vehicle will be capable of flying at speeds up to 2.4 times the speed of sound. This panel is made from the IM7 Petty 5 composite that Kathy and Roberto talked about. This panel will be tested in tension, where we can use this machine to apply up to 1.2 million pounds of force onto the panel until it breaks or fails. While we test panels here at room temperature, Ted also does thermal structural tests of smaller panels that are usually made of the same composite material.
That's right. NASA has a research program to develop a reusable launch vehicle known as the X-33 and X-34, which will be used to transport people and materials to orbit at a lower cost. In order to see how effectively adhesives and composites can work in harsh environments of space, I test relatively small samples of composite materials for liquid hydrogen propellant tanks and cyclic tests here. In one test, we use liquid nitrogen and liquid helium to cool the specimen. The panel is cooled to negative 423 degrees Fahrenheit, then a mechanical load is applied. An example of how cold liquid nitrogen is, we'll dip this carnation into liquid nitrogen and see how brittle the flowers become. In one test, we push materials to the max. We simultaneously subject one surface of the panel to minus 423 degrees Fahrenheit, while at the same time subject the other side of the panel to 250 degrees Fahrenheit. Sections of the material is then placed beneath a microscope to look for any cracks or flaws. If the flaws fall within unacceptable ranges during the time of these tests, we retest the material or even go back to the drawing board to change the fabrication process or the material.
Gentlemen, thank you so much for your time today and helping to explain to me the process of testing new materials. But now that brings me back to Van. What would you suggest Van should do with his cookies? How should he test his cookies?
Well, I think he should try a bending test performed at room temperature. That way he can see how well the cookie holds up and whether or not it crumbles.
I'll take it to extreme. You know me, Shelley. To test how well his cookie holds up, you should try a thermal dunking test. First where he dunks it in cold milk and then in hot chocolate.
Oh, those sound like some good tests. Thank you very much, and I'll report back to Van. Thanks again. And the thermal test, it went well? Great. All right, what about the bending test?
Well, I'm ready to test it now. Oh, wow, these are bending really well. I think this recipe works.
Van, I think you're forgetting the most important test.
Oh, what's that?
The taste test.
The taste test! Oh, right. Well, I'll call you back with my final results. But first, I have something planned. While I get ready for this most important test, Shelly's going back to the NASA Connect studio with some researchers who are on hand to take your phone calls and email questions about composite materials and future vehicles like the X-33. Meanwhile, I'm going to send you to Hugo A. Owens Middle School, where you'll see students from the classroom of science teacher Bernadette Smith conducting an experiment examining the strength of several materials. Follow along, and after that you'll be challenged to make your own analysis and predictions based on their results.
Hi, we're students from Hugo A. Owens Middle School in Chesapeake, Virginia. NASA Connect asked our science and math teachers, Miss Bernadette Smith and Miss Angela Williams, to have our class investigate the strength and deflection of a composite material with and without the use of a reinforcement. Ms. Smith reviews some vocabulary terms which will help us in our composite research. A polymer is a large molecule built by the repetition of small, simple chemical units. Nylon, polyester, Teflon, and rubber are examples of polymers. A fiber is a long, thin strand of material such as nylon, hair, wood, or even glass. Stress cracks are external or internal cracks in a body caused by the application of forces to the body. Maximum deflection is the largest deflection that a body or structure is allowed to take while in use before failure. Having reviewed these terms, we are now ready to divide into our research teams.
Here are the procedures we followed to do the experiment, and you can do it too. Cut out or buy 6 pieces of 8 by 15 centimeter poster board. 2 of these will be used without any reinforcement or binder. 2 will be used with the epoxy compound, and 2 will be used with the epoxy and a sheet of fiberglass. For the epoxy preparation, put on the rubber gloves and safety goggles. Then squeeze out enough of the 2-part epoxy to make a pool about the size of a quarter on the back of the poster board. Mix thoroughly with the popsicle stick. Spread the epoxy evenly over the surface of the first poster board. Take the second poster board and press the 2 pieces together. Weigh the sample down to help consolidate it. After you've done this, let the epoxy reinforced poster board dry for 10 minutes. Now we will prepare the fiberglass epoxy poster board composite. Spread the epoxy on the one side of the board with the epoxy and lay the piece of fiberglass on top of the glue. Once this is done, lay the back of the second poster board on top of the fiberglass and press to form a sandwich. The thickness of each sample is measured for the strength calculation. Our math teacher, Mrs. Williams, provides us with the numbers. While the epoxy poster board and the fiberglass board are drying, it's time to begin testing the 9 composite poster boards.
Take the 2 flat meter sticks and have them bridge a space between the 2 desks. Using the ruler, measure the inside distance between the sticks at 6 centimeters apart so they will support the poster board. This is called the span. Once you have done this, tape down the meter sticks onto the desks. Tie one end of the string onto the milk jug handle and tie the other end onto a loop big enough to slide over the lengthwise part of the poster board. Be sure to measure out enough string so that the milk jug will dangle 5 centimeters above the ground. This distance from the ground is our design maximum deflection and is the design requirement of this experiment. Now set the poster board over the meter sticks and let the jug hang down gently.
Carefully pour the water into the jug until the test material is bent enough to send the jug to the floor. Pick up the jug with the water and the string. Place these onto the scale to determine how much weight caused the poster board to bend or flex. Once we have tested the plain boards, the epoxy board, and the fiberglass board, we will compare our data with the other teams. Now we have finished our experiment, Mrs. Williams helped us to think about what our data might tell us and what mathematical statements we might write to analyze the data.
Okay, joining me in the studio are Roberta Cano, a materials research engineer at NASA Langley here in Hampton, Virginia. Also, Bill Millwood from the Space Transportation Program at Marshall Space Flight Center in Huntsville, Alabama. But before we take to our researchers and let you ask some questions, let's give you a chance to do your own computations using the data from the experiment you just saw. Then, after this segment, our 2 researchers will be answering your email questions and taking questions from our viewing audience. Okay, now, look carefully at the data and using the information in the following diagram, work with your fellow students to answer the questions as read aloud by Dr. Catherine Fay.
Based on the data presented, which specimen has the highest flex strength? Why? Based on the data presented, which specimen has the lowest flex strength? Why? Why is there such a big difference between the flex strengths of specimens 1 and 2?
Okay, we're back, and with me are Roberta Cano and Bill Millwood to answer your questions. But to start things off, Bill, let me go to you. Give us a little bit more about this X33 and X34. What is this? What are they?
Well, thanks, Shelley. It's sort of like the cookie taste test. It's the final test for new materials. Once they're developed in the lab and then tested on the ground, the next step is to fly them. And the X33 and 34 do just that. They're both unpiloted test vehicles. The X34 flies at 8 times the speed of sound. That's about 100 times faster than your parents would drive a car. And the X33 flies even faster at 15 times the speed of sound. They both will fly next year, and the materials will lead to lower cost reusable spacecraft in the future, and these future space vehicles will take us to Mars and beyond.
Wow, we are really talking about some future vehicles here then, aren't we?
That's right.
Well, we already have some email questions waiting for us. So let me go and take the first email question. That question, what are the different categories of composites? You'd probably want to take that.
Well, Shelley, there's polymer matrix composites like we saw today during the show, which are reinforced plastics. There's also reinforced metals, or metal matrix composites, and you can also reinforce ceramics. You have ceramic matrix composites. There's various types of composites you can use.
Okay, so tell us though, all these different composites, when do you know when to use which one?
Well, it depends on the application, what the application needs, what the temperature used really dictates what kind of matrix you're going to use and what kind of reinforcement.
Okay, so it's the requirements then in the application. All right, well, I understand we've got a caller out there. So caller, hey, how about giving us your first name and your question, please?
How long does it take to build new airplane material?
How long does it take to build a new airplane? Well, Bill, why don't you give us a little idea about the X33, the X34? What's the timeline on that?
Okay, these aircraft are very short, high-risk programs. Both of them were contracted for a 30-month time period, from the authority to proceed to first flight.
All right, so it'll take like maybe 2 years before we'd actually see this flying then?
3 years.
3 years,
Yes.
30 months type of thing. Okay, very good. That was an excellent question, thank you. Well, I'm going to go back to the email because we've got a couple more email questions, but call in with questions if you have them. Our second email question, how are composite materials being used with the X33? Let's go back to you, Bill.
Okay, with the X33, this is a scale model. The actual vehicle is much larger than this, and it's also larger than the X34 by a slight amount. It has 2 hydrogen composite tanks and a thrust structure. The hydrogen tanks are for the fuel.
All right, very good.
And the X-34, which will fly next May as well, it has a composite fuel tank up front and also has a structure which is the backbone of the vehicle, which is made out of composites. And these two vehicles, by having lighter weight materials that are reusable, will lead to less expensive spacecraft of the future.
All right, very good. And I understand now we've got someone else who's interested in asking some questions. So let's go back out to our viewers and our caller. Please, how about giving us your first name and your question? Is our caller there?
Yeah. My name is Trent Modesty.
Repeat the question again, please.
Okay, and my question is, how did when you put your hand in that liquid stuff, how'd you get it so cold?
Oh, okay. That's going back to where we saw Dr. Ted Johnson. He actually had some protective wear on, and he had put a flower in there, and that was maybe you'd want to answer. Do you want to answer anything about that? What he was doing there?
Well, he just stuck the flour in the liquid nitrogen, which froze it, and when he was pulling it apart, he was using a cryogenic glove, which protected his hand.
Right, so he was doing a lot of safety there. All right, let's just take one quick final email question and a quick response to this, please. What are some examples in our daily lives where composite materials are being used? Let's just have one of you.
Well, one place where composites are used is in sporting goods, in tennis rackets, and other applications where you can use these types of materials.
All right, sporting goods. All right, well, I see we're quickly running out of time. Roberta and Bill, thank you very much for joining us here today, and thanks to all the partners and guests that contributed to today's program. If you want to learn more about today's topic, visit our web panel of experts. And to try your own hand at becoming a production scientist, then jump into our online experiment, Secret Formulas. Finally, for a videotape copy of this NASA Connect show and lesson plans, contact CORE, the NASA Central Operation of Resources for Educators. For NASA Connect, I'm Shelley Canright. Hello, Dan. Hey, so tell me how'd it go? Do we have a flop or a future sensation? What? I can't hear you. What's all that noise in the background? Where are you calling from?
I enrolled at Johnson & Wales University, College of Culinary Arts in Norfolk, Virginia. I think I do have a future sensation. The jumbo jet of all cookies. The dough is prepared, the oatmeal and raisin fiber have been added, and the oven's heated, the shape is made. I think it's time for liftoff. Let's do it again. Oh, well, join us next time when we connect you to the world of math, science, and NASA. For NASA Connect, I'm Van Hughes. Goodbye. You know, you should have seen the size of the bowl I licked.